Welcome to the deep dive. I want you to do a quick experiment with me for a second, wherever you are listening to this right now. Um, just take a look around the room.
Just a quick scan.
Yeah, really scan the environment. You might see a ceramic cup resting on a wooden desk, maybe an office chair, a window letting in some light, or even just a dark shadow stretching across the floor.
Right.
Now consider how your brain instantly, without a single conscious thought, knows what all of those things are. How do you intuitively know that the coffee cup is not physically part of the desk?
Or that the shadow isn't a physical object you can bend down and pick up.
Exactly. You don't have to calculate any of this. But imagine you are tasked with teaching a machine, a completely blank, unthinking computer, to understand that exact same room.
It's a genuinely staggering conceptual problem.
Yeah.
Humans intuitively categorize the world through decades of lived physical experience. We know what a shadow is because we've interacted with light since we were babies.
Yeah, we just know.
Right, but an artificial intelligence has no physical intuition. It requires a meticulously detailed, painstakingly structured instruction manual just to comprehend the difference between a physical object and, say, the empty space right next to it, let alone more complex concepts like time or belief.
And building that ultimate instruction manual is basically our mission for this deep dive. Today, we are opening up a rather legendary stack of sources, specifically Chapter 12 on knowledge representation from a foundational text on artificial intelligence.
A very dense text.
Very dense. We are exploring the monumental effort of taking the infinite, chaotic, exception-filled reality we live in and compressing it into a format that a highly logical AI can actually process. We're talking about teaching machines how to comprehend the flow of time, the nature of physical space, how to read human intentions, and ultimately, and this is where it gets really practical, how to navigate the internet to go shopping for you.
To kind of ground this discussion for you, we are stepping into a highly specialized discipline known as ontological engineering.
Ontological engineering.
Yeah. We aren't just discussing how to write a quick script to make a robot arm move. We are discussing the attempt to represent absolutely everything in the universe so an AI can formally reason about it. It is nothing less than the attempt to create a master blueprint of reality itself.
A master blueprint of reality. That sounds incredibly ambitious, maybe even impossible.
Yeah.
The text talks about building an upper ontology. If I'm trying to picture this, I imagine my own mental filing cabinet.
That's a good way to look at it.
Right, because I don't just have a giant chaotic pile of random facts in my head. I have a structural framework. The top drawer might just be labeled anything, and as you open lower drawers, the folders get more and more specific.
That mental filing cabinet is a perfect starting point. The source text uses an analogy from object-oriented programming to illustrate this specifically, the Java Swing graphical framework.
Okay, break that down for someone who doesn't code.
Sure. When software developers build a user interface, they don't start by coding every single button and text box from scratch. They define a very broad general concept first, such as a basic window.
Just a generic window on a screen.
Exactly. They leave placeholders in that code, fully expecting that later on, other developers will define more specific variations, like a spreadsheet window or a chat window.
Oh, I see.
Ontological engineering applies that exact same logic to the universe. We define a massive, sweeping category called physical object. By establishing that upper framework, someone else can come along years later and plug in the specific logical definitions for a robot or television.
So the broadest concepts sit at the peak of the hierarchy, and the specialized concepts branch out beneath them. You are basically building the scaffolding before you worry about what color to paint the walls.
That's a great way to put it. Scaffolding first.
But the source text brings up a major roadblock here. It mentions the limitations of standard first-order logic. If first-order logic is basically the standard mathematical rulebook of cause and effect, why does it struggle to map out our reality?
It struggles because first-order logic demands absolute universal truths. It requires statements that apply to every single instance without fail. But the real world as well, it's incredibly messy, and refuses to fit into perfect logical boxes. Generalizations almost always have exceptions.
Give me an example of an exception that breaks the system.
Consider a simple rule you might want to teach. An AI tomatoes are red. That is a highly useful piece of common sense. If you ask an AI to fetch a tomato, it should look for something red.
Makes sense.
But what happens when that AI encounters a yellow tomato or a green heirloom tomato? If the system is built on strict first-order logic that firmly asserts all tomatoes are red, encountering a green one creates a catastrophic logical contradiction.
It just totally crashes the system.
The system simply fails. However, the text points out a crucial strategy here. If ontologists try to handle all that uncertainty and every possible exception right at the very beginning, they would be paralyzed.
They'd never get anything done.
Right. To successfully construct an upper ontology, we have to deliberately delay dealing with the uncertainty. We have to map out the broad, basic categories first and worry about the weird green tomatoes later.
We have to agree on the shape of the box before we argue about what doesn't fit inside it. And that idea of agreement brings up a quote from the text by a researcher named Tom Gruber that I found fascinating. He states, "Every ontology is a treaty."
A very famous quote in the field.
He calls an ontology a social agreement. I want to linger on that for a second because it implies that building AI isn't just math, it involves human compromise. Why would people have competing motives when just trying to define reality?
Because the way you categorize the world depends entirely on what you're trying to achieve.
Yeah.
Let's say you and I are building a database of vehicles. If your goal is to manage a car manufacturing plant, you will want an ontology that categorizes cars by their engine type, chassis, and manufacturing materials.
Because I need to build the physical car.
Exactly. But if my goal is to manage a government department of motor vehicles, I don't care about the chassis. I want an ontology that categorizes cars by their license plate numbers, emissions ratings, and the legal status of the owner.
So we are looking at the exact same physical object, a car, but our logical definitions are totally incompatible.
Precisely. When those competing logistical concerns outweigh the motivation to share data, a common ontology simply cannot exist. We all have different goals for our information. This is why there isn't just one single universal blueprint that all AI systems share.
It's all fractured.
Yes. But despite that difficulty, humanity has still attempted to build these massive generalized blueprints anyway. According to the text, the AI field has generally taken 4 distinct routes to accomplish this monumental task.
I want to walk through these routes because the sheer scale of the effort is mind-boggling. If we can't just wave a magic wand and have an AI understand the world, how are we actually getting the data into the machine?
Well, the first and most traditional route relies entirely on human expertise. You gather a team of highly trained logicians and ontologists, put them in a lab, and have them architect the whole system and write out the axioms by hand, line by line.
That sounds brutal.
It is. The text highlights a famous project called the CYC system, which was built primarily using this method starting in the 1980s.
That sounds like a multi-decade exercise in pure endurance, just manually typing out the rules of the universe. There has to be a faster way than that.
There is, which brings us to the second route, extracting structured facts from existing databases. Instead of writing axioms from scratch, you pull data from repositories that humans have already organized. A prime example is DBpedia.
DBpedia.
Yes, it's a system built by systematically extracting the structured data found within Wikipedia's info boxes.
So taking the thousands of hours volunteers already spent organizing Wikipedia and feeding that directly to the AI, that makes sense. What's a third route?
The third route is to unleash the machine on the unstructured web. Systems like TextRunner are designed to parse massive corpuses of raw text straight from the internet. They read millions of sentences, searching for linguistic patterns to automatically infer facts and relationships between concepts without human handholding.
It just reads the internet and tries to piece together how humanity describes the world.
Exactly.
And the fourth route is probably my favorite because it sounds incredibly chaotic. It involves crowdsourcing common sense from completely unskilled amateurs. The text mentions the open mind system, which essentially enticed random volunteers on the internet to type in everyday facts in plain English.
It is a fascinating approach. You have these 4 totally disparate methodologies, from PhDs writing strict logic in a lab, to automated web scrapers, to everyday people playing a sophisticated game of trivia.
All contributing to teaching machines what the universe contains.
Yes, and regardless of which route is taken, the very first non-negotiable step in sorting the universe is defining categories.
Let's dive into categories because the text makes a point that kind of shifted how I view my own thought process. It argues that we don't actually interact with the world by thinking about individual, unique objects most of the time.
That is a crucial insight into both human and artificial reasoning. If you decide to go to a sporting goods store, you don't walk in with the intention of purchasing one specific, universally unique object. Let's call it basketball BB9.
Right, I'm not looking for a specific serial number.
Your goal is simply to buy a basketball. You are reasoning at the level of the category, not the specific instance. Much of an AI's reasoning must take place at this categorical level to be efficient.
But how do we tell a rigid logic system to think about a broad category? I imagine a computer wants to deal with specific data points, not vague concepts like basketballs in general.
We use a vital logical mechanism called reification.
Reification.
Yes, the term originates from the Latin word res, which translates to thing. Reification is the act of taking an abstract concept or a broad category and turning it into a concrete object within the logic system itself.
Okay, how does that work?
Normally, in logic, you might use a predicate to describe a property, for instance, writing a rule that says object X is a basketball. But with reification, we turn the entire class of basketballs into an entity. We make the category itself a physical feeling object that the AI can manipulate.
Once we turn a category into a manipulatable object, what does that actually allow the AI to do?
It allows us to build taxonomic hierarchies and utilize inheritance. This is incredibly powerful. Imagine we tell the AI a core fact. All instances within the category food are edible.
Okay.
Then we inform it that the category fruit is a subclass of food. Finally, we state that apples are a subclass of fruit. Because we reify those categories, the AI automatically infers that every single individual apple in existence is edible. It inherits that property from the top down.
Oh, wow. So it doesn't need to be told that apple number 1 is edible and apple number 2 is edible all the way to a billion. It just knows.
Precisely.
And humans have been obsessed with building these taxonomies for centuries. The text points out that biologists maintain a single massive hierarchy for roughly 10 million living and extinct species, which apparently includes a truly staggering number of beetles. Or you can look at a library's Dewey Decimal System, meticulously categorizing all of human knowledge.
Those are excellent real-world examples. However, for a machine to use a taxonomy effectively, it cannot rely on intuition. We must be mathematically precise about how we slice up those categories. Ontological engineers use specific logical constraints to define the boundaries between groups. The most basic constraint is declaring categories to be disjoint.
Disjoint meaning they have absolutely nothing in common?
Correct. Two categories are disjoint if they share 0 members. For example, the category of animals and the category of vegetables are completely disjoint. There is no biological organism that is simultaneously an animal and a vegetable.
That seems straightforward enough. But the text introduces a second constraint called exhaustive decomposition. How does that differ?
Exhaustive decomposition occurs when you take a broad category and break it down into specific buckets, ensuring that every single member of the broad category fits into at least one of those buckets.
Like breaking things down into their parts.
Yes. The text uses the example of North Americans. We can exhaustively decompose the category of North Americans into Americans, Canadians, and Mexicans. Every single North American fits into one of those 3 groups.
But wait, I can spot a loophole there. What about dual citizenship? Someone can be both Canadian and American, so those buckets aren't mutually exclusive.
You have identified the exact limitation. That decomposition is exhaustive, but it is not disjoint because they share members. This brings us to the ultimate, most rigorous constraint, a partition.
The partition.
A partition happens when a set of categories is both completely disjoint, meaning 0 shared members, and exhaustive, meaning it covers absolutely everything in the broader group.
So a perfect clean slice. What would be an example of a true partition?
A classic biological example is dividing the category of animals into males and females. Every animal falls into one or the other bucket, fulfilling the exhaustive requirement. And in this specific logical model, there is no overlap, fulfilling the disjoint requirement. It is a perfectly clean partition.
Sorting things into clean buckets makes sense. But the source text throws a massive curveball when it comes to the physical composition of objects. I want to pose a question to you, the listener, that might sound a bit absurd at first. What is the fundamental logical difference between an aardvark and a block of butter?
It sounds like the setup to a surreal joke, but it actually strikes at the heart of how an AI understands physical matter. It is the distinction between things and stuff.
Things and stuff.
Yes. The English language provides a clue to this distinction through grammar, specifically the difference between count nouns and mass nouns.
Let me guess. Aardvark is a count noun because I can stand there and count them. 1 aardvark, 2 aardvarks.
Yes. You can say an aardvark, but you generally cannot say a butter or 2 butters. Butter is a mass noun. It denotes a substance rather than a discrete entity.
The text explains this with a rather visceral mental image. If you take an aardvark and cut it completely in half, you do not end up with 2 smaller aardvarks. You just end up with a biological mess.
Unfortunate for the aardvark.
Very. But if you take a block of butter and slice it in half, you still have butter. Any subpart of a butter object is still a butter object.
This phenomenon requires us to define intrinsic versus extrinsic properties for the AI. Intrinsic properties belong to the very substance of the material itself. Think of density, boiling point, flavor, or color. If you cut that block of butter in half, both resulting halves retain those identical intrinsic properties. They're still yellow, they still melt at exactly 30 degrees centigrade.
And extrinsic properties are the opposite.
Extrinsic properties belong only to the object as a complete unified whole. Examples include weight, length, or shape. If you cut the butter in half, the weight of each piece changes, the shape changes. Therefore, in our ontology, stuff is the most general category for substances defined purely by intrinsic properties, whereas thing is the most general category for discrete objects defined by their extrinsic properties.
Okay, I want to test this logic. What if I go to the grocery store and put 3 individual apples into a plastic produce bag? Each apple is a distinct thing, but sitting there in the bag, together they weigh exactly 2 pounds. Now, I know from basic math that a set is an abstract concept, and an abstract concept cannot have physical mass. So how does the AI logically comprehend the physical weight of a collection of distinct things?
The AI cannot weigh a mathematical set, so the text introduces a specialized concept called a bunch.
A bunch.
A bunch is a composite physical object that has those specific apples as its constituent parts, but it lacks any formal structure. A bunch of apples is not an organized system, it's just a grouping.
By calling it a bunch, we trick the AI into treating it like a single physical item.
Exactly. It allows the reasoning system to treat the chaotic collection as a normal, tangible object that can possess an extrinsic property like weight. To define this rigorously, the system uses a process called logical minimization. It formally defines the bunch as the absolute smallest physical object that contains all of those specific parts and absolutely nothing else. It draws a tight logical bounding box around the apples.
I am continually amazed by how granular we have to be to make a computer understand reality. But let's pivot back to those exceptions we talked about earlier, the green tomatoes. We've established how to rigidly sort things, but how do we define an object when it refuses to conform?
That's where it gets complicated.
Think about the concept of a game. The philosopher Wittgenstein is brought up in the text, and he pointed out that chess, tag, solitaire, and professional basketball are all games. But try to write a single strict definition that covers all of them. You can't. There is no universal trait. They just share what Wittgenstein called family resemblances.
This is a classic dilemma known as the problem of natural kinds. The vast majority of categories in the physical world do not possess strict, mathematically clear-cut definitions. You cannot write a perfect logical formula for a tomato. So the strategy in knowledge representation is to bifurcate the definition. We separate what is unequivocally true of all instances from what is only true of typical instances.
So we create a special subcategory for the ideal version of the object.
Precisely. We create a category designated as typical tomatoes. We program the AI with the knowledge that a typical tomato is dull scarlet in color, roughly spherical in shape, and roughly 2 to 4 inches across. This provides the AI with a functional statistical baseline to operate from, even if it eventually encounters a fuzzy yellow tiny tomato later on.
The text also mentions the philosopher Quine, who challenged the idea of strict definitions from a linguistic perspective. He looked at the definition of a bachelor. A bachelor is an unmarried adult male. That seems like an airtight, perfect, logical definition. But Quine asks, what happens if you apply that to the Pope?
It creates a fascinating friction. Logically and technically, based on the rigid definition, the Pope is absolutely a bachelor. He's an unmarried adult male. But as the text notes, using that term for the Pope is infelicitous.
Infelicitous, that's a great word. It basically means it's deeply weird.
It is weird because human language carries immense cultural baggage. Calling someone a bachelor implies they are eligible to date or perhaps participating in a certain lifestyle. The Pope is not doing those things. This demonstrates that strict logical definitions, while necessary for a machine's internal database, will inevitably clash with the fluid, context-heavy nuances of human conversation.
The AI has to balance strict math with human vibes. Speaking of things that are hard to quantify with math, let's talk about measurements. We can easily feed an AI numerical data. A $1 bill equals $1. A basketball has a diameter of 9.5 inches. But reality isn't just inches and dollars. What about subjective measures? How does an AI calculate the deliciousness of a slice of cake or the difficulty of a math test?
You cannot easily attach a numerical scale to subjective experiences or complex physical interactions. But an AI still requires a mechanism to reason about them. The source text provides an elegant example regarding academic exercises. Suppose you are aware that exercises written by Peter Norvig are generally much tougher than exercises written by Stuart Russell.
If I know Norvig's are harder, I don't need to know that Norvig's difficulty level is an 8.4 and Russell's is a 6.2. I just know I'm probably going to get a lower grade on the Norvig test.
Exactly. You don't need specific numerical values. You merely need the ordering. You just need to know the relational truth that A is greater than B. This concept forms the foundation of a subfield known as qualitative physics.
Qualitative physics.
It empowers an AI to reason about physical systems and the monotonic relationships among different measures without requiring it to plunge into computationally exhausting equations or granular numerical simulations. It can make qualitative judgments.
So we have successfully mapped out the static universe. We have reified objects, we understand the difference between stuff and things, and we can measure them qualitatively. But the universe isn't frozen. Things move. Things happen. How do we teach an AI about time, space, and events?
To understand the modern approach, we must first look at the limitations of older AI models, specifically situation calculus. In situation calculus, actions were modeled as discrete, instantaneous state changes. Imagine an AI observing a bathtub being filled. The situation calculus model understands the initial state tub is empty, then an action occurs. Then it understands the final state tub is full.
But it completely ignores the actual process of the water flowing. It's like a strobe light, flashing, empty, flash, full.
That is a perfect analogy. It is completely blind to duration. Furthermore, because it only processes instantaneous state changes, it is entirely incapable of handling simultaneous events. If you ask an AI using situation calculus to brush its teeth while the bathtub is filling, it simply cannot compute the overlapping timelines.
That is a massive blind spot for any robot trying to operate in the real world. So how did researchers solve the strobe light problem?
They developed event calculus. And to make this work, we have to employ that reification trick we discussed earlier. We must turn the events themselves into tangible objects within the logic system.
Okay.
Let's use an example from the text. A man named Shankar is flying from San Francisco to Washington, D.C. In event calculus, we create a specific object representing that flight. And because the flight is now an object, we can attach properties to it. We can inform the AI that Shankar's flight was bumpy.
You couldn't tell the situation calculus that the flight was bumpy because in that model, the flight didn't have a duration. It was just in San Francisco, flash, and Washington, D.C. By making the event an object, we can describe its qualities over time.
Precisely. And just as we distinguish between things and stuff in the physical realm, event calculus forces us to distinguish between different types of events. Shankar's complete trip from San Francisco to D.C. is classified as a discrete event. It has a defined, rigid structure, a specific beginning, a middle duration, and a specific end. If you interrupt that flight halfway through, say, the plane is diverted to Kansas, it is no longer a trip to D.C., the essential nature of the event has been destroyed.
But what if we zoom in? What if the AI only analyzes a 20-minute slice of that flight? Let's say the 20 minutes where Shankar is sitting in his seat, staring out the window, waiting for the flight attendant to bring him a bag of peanuts.
That isolated 20-minute slice is still an active instance of the category of flying. Categories of events that possess this unique property where any internal subinterval of the process is fundamentally the same as the overall process are called liquid events or processes.
Liquid events. I love that terminology.
They are essentially temporal substances. Remember how cutting a block of butter in half gives you more butter? Taking a temporal slice of a liquid event still gives you that exact same event. The act of flying is the temporal equivalent of physical stuff.
So to manage these discrete and liquid events, the AI needs a calendar. It needs a way to understand time intervals. The text breaks this down by distinguishing between moments, which mathematically have absolutely zero duration, and extended intervals, which do. And it references a specific logical framework proposed by a researcher named James Allen, which outlines 13 distinct interval relations.
Allen's 13 interval relations provide the AI with a rigorous vocabulary for chronological context. They define exactly how two distinct intervals of time interact with one another. Let's look at a relation called meets. In this logic, two intervals meet if and only if the exact end time of the first interval is the exact start time of the second. There is zero gap and zero overlap.
To make that concrete for you listening, think of British monarchs. The reign of Queen Elizabeth II meets the reign of King George VI. The very second his reign ended, hers began.
Another crucial relation is overlaps. Now, in casual human conversation, we often think of overlapping as a symmetrical two-way street. But in Allen's specific logical definitions, interval only overlaps interval j if I begins before j begins and continues into it.
The text gives a great cultural example for this. The reign of Elvis Presley overlaps the 1950s. Elvis became active before the decade of the 50s officially began, and his cultural reign continued deeply into and through that decade.
And defining time so precisely brings us to a rather profound, almost mind-bending philosophical consequence of this entire framework. If a physical object is, fundamentally, simply a chunk of space-time whose properties might change over a duration, then we can view all physical objects as generalized events.
Wait, hold on. Let me make sure I'm grasping the scale of what you're saying. Are you telling me that from the AI's perspective, I am not a thing? I am an event. Is the coffee cup on my desk currently happening as an event?
Within this specific ontological framework, yes, you are a localized event occurring in space-time. To illustrate this, the source text uses the United States of America as a prime example. The AI views the USA as a continuous, massive event that began in 1776 and is still currently in progress. It is a hyper-object stretching across centuries. Its properties fluctuate, the population grows, the physical borders expand or contract, and it possesses one highly specific property that changes every 4 to 8 years, the president.
Okay, this is where my brain starts to hurt. If the AI views the USA as one continuous, unbroken event, how does it process the concept of the president? Because standard logic demands that a specific term denotes exactly one unique object. The AI can't use the term the president and mean George Washington one minute and Abraham Lincoln the next without causing a massive system error.
To resolve this, the ontological system treats the term President USA as denoting a single, massive hyperobject that consists of different biological humans at different temporal intervals. It is a composite object made up of George Washington from 1789 to 1797, seamlessly spliced together with John Adams from 1797 to 1801, and so forth.
It's like a Voltron made of historical figures.
Exactly. So when the AI evaluates a historical statement about the president in the year 1790, it is checking for an identity match between the specific sub-event of that hyperobject covering 1790 and the distinct object of George Washington.
That is an incredibly complex yet elegant way to handle the passage of time. So we've taught the machine how to comprehend a bumpy flight across the country, the physical nature of a block of butter, and the century-spanning hyperobject that is the U.S. presidency. But now we arrive at a completely different kind of challenge. We have to teach the AI how to read minds. Or, more accurately, how to think about the process of thinking.
This is a critical evolutionary leap for an AI. To be truly useful, an AI must possess knowledge about beliefs and knowledge about deduction. It needs an awareness of what it knows, and just as importantly, it must be able to model what other independent agents know.
I really appreciate the scenario the text poses to explain why this is necessary. Imagine you are sitting at a table and someone walks up to you and asks, "What is the square root of 1764?" You might initially say, "I have no idea." But if they tell you to think harder, and you sit there with a pencil and crunch the numbers, you might actually deduce the answer. Deduction works there.
Yes, mathematical deduction.
But what if they walk up and ask, "Is your mother sitting down right now?" Thinking harder isn't going to accomplish anything. You can't deduce that. You either know her current state or you don't. The AI needs to recognize the difference between a problem it can calculate internally and a problem that requires it to seek outside information.
To build that awareness, ontological engineers introduce propositional attitudes. These represent the specific attitudes an intelligent agent can hold toward mental objects or propositions. We introduce predicates like believes, knows, wants, or intends. However, the moment we introduce these, we realize they do not behave like the normal logical predicates we use for physical objects. This behavioral difference introduces a famous complication known as the Superman paradox.
Ah, the Superman paradox. This is a classic thought experiment. Let's unpack this for the listener. Imagine the fictional universe of Metropolis. We have Lois Lane. Lois Lane knows for an absolute fact that Superman can fly. We also know a second absolute fact. Superman is the exact same biological entity as Clark Kent. Therefore, if we feed this into a standard logic system, the AI deduces that Lois Lane knows Clark Kent can fly. But wait. Anyone who has read a comic book knows she doesn't. She has no idea Clark is Superman. Our rigidly logical AI just arrived at a completely false conclusion about human knowledge.
The AI arrived at that false conclusion because standard first-order logic operates on a strict principle called referential transparency. Under referential transparency, if two different terms refer to the exact same physical object, like the terms Superman and Clark Kent, You can swap them out interchangeably in any sentence, and the truth value of that sentence remains identical.
Which is normally exactly what we want the computer to do, right?
Yeah.
If the AI knows that 2 plus 2 equals 4, and it knows that 4 is less than 5, we absolutely want it to seamlessly substitute those terms and deduce that 2 plus 2 is less than 5.
Exactly. For math and physical objects, transparency is essential. But for propositional attitudes, when we start using words like believes or knows, that interchangeability utterly destroys the psychological reality of the situation. To fix this, we must abandon referential transparency and implement what is known as referential opacity.
Referential opacity, meaning the specific words a person uses in their head actually matter. It matters immensely that Lois conceptualizes him as the word Superman and not the word Clark. So how does an AI compute opacity? It sounds like we have to rewrite the rules of logic.
We essentially do. We have to move beyond standard logic and introduce modal logic. Regular logic deals with only a single objective modality, absolute truth. Modal logic introduces special operators, most notably the knowledge operator, which is typically represented by a capital K. This allows us to write formal sentences that specifically translate to Agent A knows proposition P. And the underlying mathematics of this are vastly more complex. We no longer operate within one single universally true world model. We now have to compute a vast collection of possible worlds.
Okay, let's try to visualize these possible worlds. Imagine drawing a graph on a whiteboard. You draw a series of bubbles, and every single bubble represents a different possible reality. And these bubbles are connected by lines or arrows, which is the text refers to as accessibility relations. If an arrow points from World 1 to World 2 for Lois Lane, it signifies that based strictly on the limited information Lois possesses in World 1, World 2 is a perfectly valid, logical possibility in her mind.
To truly grasp how complex this gets, we should walk through the weather report diagrams provided in the source text. These diagrams map out the overlapping accessibility relations for both Lois and Superman regarding two specific unknown propositions, whether a weather report is predicting rain and whether Superman's secret identity is exposed.
Let's take this slow and look at scenario 1. In this starting possible world, Lois has not seen the weather report, so she doesn't know if it will rain. Furthermore, she does not know that Clark is Superman. So from her perspective, looking at her graph, there are 4 accessible worlds she considers possible. A world where it rains and Clark is Superman. A world where it rains and Clark isn't Superman. A world where it doesn't rain and Clark is Superman. And a world where it doesn't rain and Clark isn't Superman. She's completely in the dark on both issues. But, and this is the crucial part, she does know that Superman himself knows his own identity.
That is where the graph becomes multidimensional. In every single one of those 4 worlds accessible to Lois, Superman either knows he is Clark or he knows he isn't. Lois doesn't know which of those worlds is the actual true reality. But because that specific truth that Superman knows who he is holds firm in all of her accessible worlds, the AI securely deduces that Superman knows his own identity.
It's deducing knowledge based on the boundaries of her ignorance. Okay, let's complicate it with scenario 2. This time, Lois has seen the weather report. She definitively knows it is going to rain. Superman, however, has not seen the report, so his graph of accessible worlds includes both rain and no rain, but he watched Lois watch the report. He knows that Lois has seen it.
So analyze Superman's accessible worlds. He considers a world where it rains, and in that world, Lois knows it rains. He considers a world where it does not rain, and in that world, Lois knows it does not rain. He himself doesn't know what the weather will be, but the AI can deduce that he knows that she knows.
And then the text unleashes scenario 3, which combines everything into a tangled web. Superman knows his own identity, but he has no idea if Lois has seen the weather report or not. Meanwhile, Lois has seen the weather report, but she doesn't know his identity.
In this scenario, Superman's graph of possible worlds expands dramatically. From his singular starting node, his accessibility relations force him to entertain worlds where Lois knows it will rain, completely separate worlds where she knows it won't rain, and yet another set of worlds where she doesn't know the weather either way. The AI has to track all of these branching hypothetical realities simultaneously just to understand a simple interaction between two people.
It's like the movie Inception, but built entirely out of mathematical logic. And what's amazing is that this modal logic actually solves another notorious problem with human language, the ambiguity of quantifiers. The text brings up a classic spy example. James Bond knows someone is a spy. If a human reads that English sentence, it can be interpreted in 2 completely different ways. It could mean Bond knows exactly who the spy is, like he's staring across a baccarat table directly at Le Chiffre.
Or, that exact same sentence could merely mean Bond has deduced that at least one spy exists somewhere in the casino. but he has absolutely no idea which specific person it is. Standard logic struggles with this ambiguity. Modal logic clarifies it effortlessly by looking at the possible worlds. In the first interpretation, there is a specific individual X, and in all of Bond's accessible worlds, that exact same X is the sky. In the second interpretation, in every accessible world, there is someone who is a spy, but the identity of the spy changes depending on which world you look at.
It's a brilliant solution, but of course nothing is perfect. The text notes a massive glaring flaw with modal logic called logical omniscience. What happens when this system breaks down?
The breakdown occurs because of the sheer computational weight of the system. Modal logic mathematically assumes that if an intelligent agent knows a base set of axioms, that agent instantly, automatically, and effortlessly knows all of the infinite mathematical and logical consequences of those axioms.
So if I know the basic rules of how chess pieces move, modal logic assumes I simultaneously know every single possible winning strategy in the history of the game.
Exactly. It assumes infinite deductive capacity. This obviously does not map to how human psychology works, nor does it map to physical computers constrained by processing power and memory limits. We simply do not have infinite time or energy to deduce every single consequence of our knowledge base.
Which brings us to a massive logistical hurdle. How do we actually build the brain's filing cabinet so that it is efficient? We need reasoning systems that don't get paralyzed, stuck in infinite loops of deduction trying to figure out every possible world. This brings us to the history of semantic networks. Picture the philosopher Charles S. Peirce, way back in 1909, sketching out what he called existential graphs. It's essentially a system of bubbles and arrows.
While they look like simple diagrams, these visual representations are a rigorous form of logic. A semantic network utilizes nodes, the bubbles, to represent specific objects or broad categories. It then uses labeled links, the arrows, to represent the relationships between them. So you might create a node for an individual named Mary, another node for John, and draw a link labeled sister off, pointing directly from Mary to John.
And the text points out that the structure handles that crucial concept of inheritance we talked about earlier beautifully. Let's say the AI needs to answer a simple query. How many legs does Mary have? In a standard database, it might have to search through millions of lines of code, but in a semantic network, it just physically follows the arrows. Mary's node has a link pointing up to the broad category of persons, and the persons category has a special boxed link attached to it pointing to the number 2 for legs. The AI follows the path, hits the number 2, and boom, it knows Mary has 2 legs.
It is incredibly fast. However, the source text adds a very strict, important caveat about how ontological engineers are allowed to draw these links. For instance, we can legitimately draw a link, labeled hasmother, from the individual node Mary to the individual node Susan, but we absolutely cannot draw a hasmother link originating from the abstract category of persons pointing to the category of female persons.
Why is that forbidden? Don't all persons have mothers?
The individuals do, but the category does not. Categories are abstract mathematical concepts. They do not have mothers. If an engineer isn't careful with their semantics and draws that link, they would accidentally be telling the AI that the abstract concept of a person was literally biologically birthed by the concept of a female. To avoid this, we have to use highly specific notation to assert that every member within a category has a mother, rather than applying the property to the category itself.
That makes perfect sense. The abstraction doesn't have DNA. But what happens when the AI follows these links and shits a real-world exception? We establish that the category of persons has a link to 2 legs, but the text uses the example of Long John Silver, the famous pirate. He famously only has 1 leg. If our semantic network is too rigid, telling the AI that Long John Silver is a person creates a fatal logical contradiction that could crash the system.
This specific scenario is where semantic networks truly shine compared to older logics. They inherently allow for default values. The assertion that persons have 2 legs is granted default status, rather than absolute universal status. When the AI's inheritance algorithm starts at the Long John Silver node to determine his leg count, it begins following the links upward toward the person's category. But if it immediately encounters a link attached directly to Long John Silver asserting 1 leg, the algorithm is designed to stop looking.
It accepts the local truth and ignores the overarching rule.
Exactly. The specific, localized information overrides the general default. This architecture is vastly simpler and more elegant than forcing a programmer to write complex, convoluted logical exceptions into the main rulebook for every single one-legged person who ever existed.
It prioritizes speed and efficiency. But drawing bubbles and arrows isn't the only way to build these networks. The text introduces a text-based alternative to the visual graphs, known as description logics. It specifically mentions a language called classic.
Description logics evolved directly from semantic networks, with the goal of formally standardizing the definitions of categories. Instead of relying on visual graphs, which can sometimes become messy or ambiguous, they use a strict algebra of operations. But their true superpower, which the text heavily emphasizes, is a property called tractability.
Tractability. I've heard computer scientists use this word. It essentially means the AI can actually finish solving the problem before the heat death of the universe, right?
That is a colorful but accurate way to put it. Standard first-order logic systems can easily fall into potentially exponential computational loops. If you ask them a complex question, they might take weeks or years to calculate the answer. Description logics forcefully prevent this by strictly limiting the vocabulary of the language itself.
Can you give an analogy for what polynomial versus exponential time feels like? Why is limiting the language so crucial?
Imagine you were trying to find a specific person's phone number. If you have an alphabetized phone book, finding the number takes a predictable, relatively small amount of time, even if the book is large. That is manageable. That is akin to polynomial time. But imagine if the phone book was completely randomized, and every time you checked a name, the entire book reorganized itself. Searching it would take an impossibly long time, expanding exponentially. By restricting what the AI can say, for instance, by forbidding the use of the negation operator or operator description logics, guarantee that the AI can answer subsumption questions like, is category X a subset of category Y in fast polynomial time? The engineers purposefully trade away expressive power in exchange for a cast-iron guarantee of processing speed.
They put blinders on the AI so it runs faster in a straight line. Okay, so we've established a fast system that utilizes default values. I want to dive much deeper into this idea of defaults because it fundamentally changes how logical reasoning operates. It introduces the art of jumping to conclusions, and this brings us to a complex concept called non-monotonicity.
To truly appreciate non-monotonicity, we have to contrast it with classical mathematics and logic, which are strictly monotonic. In classical monotonic logic, if you learn a new, verified fact, your overall set of beliefs grows larger. Everything you previously knew remains absolutely true. You simply possess more knowledge. The size of your knowledge base only ever goes up.
But human beings do not operate like that at all. The text gives a fantastic, relatable analogy. Imagine you are walking down the sidewalk and you see a car parked on the street. Because of the angle you are walking, you can only visually see 3 of its wheels. Despite that lack of visual evidence, your brain immediately jumps to the conclusion that the car has 4 wheels. You assume it. You don't need to call a mechanic to sign a sworn affidavit confirming the 4th wheel exists. Your belief is firmly set.
Your brain applies a default assumption based on typicality.
Exactly. But then, imagine the scenario changes. Suddenly, you see the car's owner walking away down the street carrying a tire, and you notice the car is actually propped up on a metal jack. Instantly, your internal belief system shifts. You retract your assumption about the 4 wheels. Your total set of beliefs didn't just grow, it shrank. You actively abandon a fact you previously held to be true.
That act of retraction violates the core tenet of classical logic. That is the essence of non-monotonicity. Because classical logic couldn't handle this human-like reasoning, AI researchers were forced to develop entirely new logical frameworks. One of the most prominent is called circumscription. The foundational premise of circumscription is to instruct the AI to assume that things are as false as possible.
Assume things are as false as possible. What does that mean in practice?
We introduce a specific logical predicate to represent being abnormal.
Mm-hmm.
So we might write a rule that states, a bird flies, unless it is abnormal. A circumscriptive reasoning system will look at an object, say, sparrow, and will automatically assume that the sparrow is not abnormal unless it is explicitly fed data proving otherwise. It seeks to minimize the number of abnormalities in its worldview.
It assumes normalcy until proven weird. But what happens when 2 perfectly valid default assumptions violently collide with each other? This creates a famous paradox in AI architecture known as the Nixon diamond. Let's look at the historical figure of Richard Nixon. We have fact 1, he was a Quaker. The default typical rule for Quakers is that they are pacifists. We have for fact 2, he was a Republican. The default typical rule for Republicans is that they are not pacifists. So if we feed this into the AI, what does it do when the defaults contradict? Does it crash?
A non-monotonic logic system is sophisticated enough not to crash. Instead, it handles the contradiction by generating multiple preferred models or extensions of reality. It essentially splits its reasoning. In one preferred model, it minimizes the abnormality regarding his Quaker heritage and concludes he's a pacifist. In the alternate model, it minimizes the abnormality regarding his Republican affiliation and concludes he is not a pacifist. The AI essentially shrugs its metaphorical shoulders and remains perfectly agnostic. It acknowledges both realities are possible based on the defaults. It holds both thoughts in its head simultaneously, but what if we need an answer? If a definitive answer is required, engineers introduce prioritized circumscription. This involves explicitly programming the AI with a tiebreaker hierarchy. For example, an engineer could program a meta rule stating that, in this specific database, religious beliefs always override political beliefs. If that priority is set, the AI will consistently choose the pacifist model. There's also another formalism called default logic, which handles this by explicitly writing rules with three parts: prerequisites, justifications, and conclusions.
Give me an example of a three-part rule.
It would read something like, if X is a bird, which is the prerequisite, and it is logically consistent with our current database to believe X flies, which is the justification, then officially conclude X flies. But implementing any of these non-monotonic systems introduces a massive logistical nightmare when an AI is faced to retract a belief.
Right, because beliefs are interconnected. Think back to the parked car. If the AI firmly believed the car had four wheels, and based on that belief, it planned a cross-country road trip, and based on the road trip, it booked non-refundable hotel rooms. The moment it realizes the wheel is missing, it has to undo all of those cascading decisions. It's like pulling a loose thread on a knitted sweater. The whole structure can unravel instantly. How does a computer possibly keep track of that web of assumptions?
Managing that web is the sole job of truth maintenance systems, or TMS. The most basic version is a JTMS, a justification-based truth maintenance system. It solves the unraveling problem by mandating that every single fact generated in the database has a specific justification rigidly attached to it. It tracks the lineage of every thought.
So if a core fact is proven false, it knows exactly what to delete.
It doesn't even delete them. If you retract a core fact, the JTMS quickly scans its dependency graph and retracts only the specific downstream facts that relied exclusively on that retracted premise. And instead of erasing them from the hard drive, it simply marks them as out of the current logical game.
It benches them, like a player in a basketball game. Because if the mechanic suddenly walks out of a shop holding a brand new tire, the AI can instantly put all those facts back in the game without having to recalculate the road trip and the hotels from scratch. It saves an unbelievable amount of computing power.
Exactly. And the technology goes even further. There is a more advanced iteration called an ATMS, an assumption-based truth maintenance system. This system is revolutionary for hypothetical, forward-planning reasoning. The source text illustrates this with a massive logistical scenario. The Romanian Olympic Committee planning the facilities for the 2048 Olympic Games. They have to evaluate different host cities: Pitești for swimming, Bucharest for athletics, and Arad for equestrian events.
Planning an Olympic Games is a staggeringly complex web of variables. You are calculating traffic flows, hotel capacities, security deployments, electrical grid usage. It's millions of data points dependent on where the events are held.
Precisely. Now imagine the committee is deep into the planning process and they want to consider a massive hypothetical pivot. What if they abandon Bucharest and decide to use the city of Sibiu for athletics instead? In a standard, older reasoning system, calculating that change would require wiping the slate clean and starting the millions of calculations entirely from scratch.
Which would take forever. How does the ATMS avoid starting over?
An ATMS is capable of representing multiple conflicting states of reality simultaneously. It meticulously tracks which specific underlying assumptions make which resulting sentences true. By simply switching the core assumption tag from Bucharest to Sibiu, the ATMS instantly shifts the entire context of the database. It recalculates the athletics logistics for Sibiu while flawlessly preserving all the complex underlying logic for the swimming events in Pitești, because it knows the Pitești data wasn't dependent on the Bucharest assumption.
It's like having multiple parallel dimensions open on your computer screen at the same time, and you can just effortlessly hop between them to see how things play out. And the text notes that the ATMS also gives the AI a crucial ability for interacting with humans, the ability to generate explanations for why things happen.
Yes, tracing the lineage of facts works in reverse as well. If an AI diagnoses that a car won't start, the ATMS can look at that final end-state node car won't start and trace the arrows backward through the dependency graph to find the root assumptions that logically lead to that state, such as gas tank is empty or battery is completely dead. It grants the AI the power to explain its own internal reasoning process to a human user.
And that ability to reason dynamically, explain its logic, and rapidly manage shifting assumptions is exactly what we need to finally take all this dense theory and put it to work in the real, messy world.
Which brings us to the culmination of all these systems operating in tandem.
Our grand finale, the ultimate AI shopper. We are going to apply everything we've unpacked today, the upper ontologies, the rigid categories, the event calculus of time, and the non-monotonic default logic to an AI whose sole mission is to buy you a digital camera or a new laptop on the internet.
The internet is the ultimate stress test for knowledge representation because it is the exact opposite of a clean, mathematically sound textbook. It is a wildly chaotic, constantly shifting array of raw HTML strings, broken JavaScript, malformed code, and deliberately deceptive marketing layouts.
It's the wild west of data, so let's boot up our AI shopper. Step 1. It has to follow hyperlinks to actually locate the products. It needs to know how to navigate from a massive retailer's homepage down into the specific product offer.
This navigational task relies entirely on the precise taxonomic hierarchies we discussed in the beginning. The AI must possess an internal map. It needs to know that a laptop is a designated subcategory of computers, which in turn is a subcategory of electronics. When the AI scans the raw code of a web page, it evaluates the anchor text of the hyperlinks to see if they logically map to its internal hierarchy.
But this is where the messiness of human language creates a nightmare. The AI constantly runs into issues of synonymy and ambiguity. A specific online store might label their section notebooks instead of laptops. Or consider an even worse scenario. What if the AI encounters a link that simply says CDs? Does that refer to a music compact disc? Or does it refer to a financial certificate of deposit from a banking institution? If our AI is trying to buy a stereo system, it requires an incredibly rich, nuanced vocabulary to know which CD link is the correct path.
To manage the sheer, overwhelming scale of the internet, the system employs a technique called procedural attachment. It would be computationally impossible to download the entire contents of the internet into the AI's internal knowledge base. So instead, it treats the live external internet as if it were a seamless extension of its own mind. When the logic system reaches a point where it desperately needs to know the contents of a specific web page, it pauses its internal deduction, executes a live HTTP procedure to fetch the page in real time, extracts the data, and then resumes reasoning.
So the AI successfully navigates the chaotic links and locates 3 different store pages, all selling laptops. Now it faces the hardest part, comparing the offers. The price of the laptop isn't neatly labeled with a perfect logical tag that says price equals X. It's just stylized text scattered on a screen IBM ThinkBook, our amazing price, $399. How does the machine extract the actual mathematical value from that marketing fluff?
It utilizes specialized subprograms known as wrappers. Wrappers are algorithms specifically designed to parse the raw, messy HTML of a web page and surgically extract specific vital data points, the exact price, the CPU speed in gigahertz, the memory size in gigabytes. Once extracted, the wrapper translates those points back into the AI's internal knowledge base as formal, logical assertions that can be mathematically compared.
So the wrappers successfully do their job, they pull the data, and we set up a showdown. We have 3 laptops in our cart. Laptop A is priced at $299 and features a 1.4 gigahertz processor. Laptop B is priced at $500, features a slower 1.2 gigahertz processor, but it boasts significantly more RAM. Finally, laptop C is priced at $399 with a 1.2 gigahertz processor. How does the AI logically decide which one is the best?
It employs a decision-making matrix looking for dominated offers. A dominated offer is defined as an option that is definitively, mathematically worse than another available option on at least one key attribute and no better on any other attribute. Let's compare laptop C, which is $399 and 1.2 gigahertz, against laptop A, which is $299 and 1.4 gigahertz. Laptop A is both cheaper in price and faster in processing speed. Therefore, laptop A entirely dominates laptop C. The AI can confidently and permanently eliminate laptop C from consideration.
We throw laptop C in the digital trash, but what happens when it compares laptop A versus laptop B? Laptop A is cheaper and faster, but laptop B has that massive upgrade in memory.
In this comparison, neither A nor B strictly dominates the other. They present clear trade-offs. Because the AI does not inherently know your subjective personal preference, it doesn't know if you value processing speed for gaming over storage memory, for video editing. It will not make the final choice for you. Instead, it will present both laptop A and laptop B to you, categorizing them as the optimal undominated options. It functions as the ultimate, perfectly logical personal shopper, aggressively filtering out the objectively bad deals and handing you the mathematically sound choices.
That is an amazing culmination of everything we've covered. We have taken quite a journey today through the architecture of artificial thought. We started with abstract philosophical debates about whether a green tomato breaks the laws of math and whether the physical nature of an aardvark differs from a block of butter. We figured out how to use possible worlds to read Superman's mind. We learned how to pull the sweater thread of logic when jumping to conclusions about missing car tires, and we ended up with an AI dynamically traversing the internet to buy you the perfect laptop.
It truly highlights the incredible, often invisible complexity of what human beings casually refer to as common sense, and the monumental, history-spanning engineering effort required to translate that human sense into a formal structure a machine can utilize.
It absolutely does. And as we wrap up this deep dive, I want to leave you, the listener, with a final thought to mull over. We talked early on about Tom Gruber's concept that every ontology is a treaty, a social and logistical agreement about how to categorize the physical world based on what we need from it. Think about the countless objects and processes in your own life. What happens in the near future when two incredibly powerful autonomous artificial intelligences, built by completely different global corporations with completely different logistical ontologies and structural agreements about what stuff or events are, have to interact and negotiate with each other at lightning speed? If we, as humans, still struggle to define what a game is, or if calling the Pope a bachelor makes sense, how will a fleet of autonomous machines ever successfully agree on how to categorize, share, and navigate the physical world they share with us?
That structural negotiation is the true uncharted frontier of ontological engineering.
It is definitely something to ponder the next time you look around your room and effortlessly know what a shadow is. Thanks for joining us on this deep dive. Keep questioning the invisible structures of the reality around you, and we'll catch you next time.